Hello, everyone. Yeah, today let's look at hash collisions. So hash collisions uh, is a very is one of the first thing I dealt with when you started to extend from file format tricks um, to what can I say to cryptography. And so basically, people have some constraint, cryptographic constraints, hash collisions, and other things. And then they're like, hey, there's nothing we can do here. What about going to the next step, And this is exactly what happened before. Not exactly a hash collision. It was a collision, but maybe not the one that you expect. In 2014, so let me share my. And in 2014, I like that the screen was still in 430, 430, the ratio. Um, the I started to collaborate with Jean-Philippe Aumasson. Jean-Philippe Aumasson, VORC, is the one who reached out to me, and then mostly with Maria Eichelzeder about a modified SHA-1 collision. And and then so that was in 2014. Then I joined Google in 2015, and then in 2017 we released the first SHA-1 collision, Shattered. And then I presented about the details of this thing, of the hash collisions, and then with the help of Mark Stevens, the author of the Shattered, of the whole paper behind the SHA-1 collision, but also the many things about MD5 collisions. Then I presented on that, and actually there should be a screenshot of me, and there should be anyway you of me and Mark. And then I did a presentation about. Then I started working more on hash collisions with the help of Mark, and then started to really try to kill MD5 wherever it was hiding. In all kinds of file formats. Was it possible or not? Then I started a workshop on exploiting hash collisions, which I call Colltris, and then I eventually so I created a repository that is has all many knowledge and files, examples and complete theory and whatever. And it's not super up to date, but at least you will have a lot of scripts that are ready collisions that you can learn. We will actually use it today, that you can learn with existing colliding files of every file types. Sometimes they have examples, sometimes they are just very tiny collections of actual the scripts themselves, to with the computed prefixes. We will see what it means, even the way to include a hash collision in a the include a SHA-1 collision in your in your LaTeX documents, and also hash coins, which is a very interesting way of abusing hash collisions, which we'll cover today if we have time. And there should be also, where is it, a workshop? No, there's no workshop. Oh yeah, there is a workshop, and the workshop showing some examples of the files and even the prefixes if you just want to study the prefixes themselves, like pure examples. So basically, this is the base of the research, the workshop that I did, but it actually contains more. Now it contains hash coins, it contains a bit more. It's not super up to date, but definitely it has 3,000 stars. It's it's decent. Let's put it that way. I made it decent. And then after that, as I presented the Colltris workshop a couple of times, maybe it's a bit outdated, this list. And then I was reached out to abuse two interesting file formats, which were a bit more tricky to abuse with hash collisions, which we will cover today if we have time. No questions? So, okay. So I'll follow the Colltris slides because I made them very accessible from the very beginning. So the slides are online, of course. And let's go. So Hash collisions is often misunderstood. Like MD5 is broken, just don't use it, and it always takes hours, which is wrong. And now there are several speeds of hash collisions, and it depends which one you want to use or not, which one you should use, what are the impact, what the possibilities, and so on. And yeah, so let's start. And the usual mistake is that when you have a hash, so there's a number, and then it return a big number that is always different. And if you slightly modify the number, the hash, the original content, the resulting number is completely different. Now, a very important thing is that why is there an extra digit here? That's a bit of a problem. I never noticed. There's an extra digit in this MD5. This is weird. Okay. And the thing is, if you cannot guess a content from its hash value, it's extremely rare, even from arbitrary hash, or to replicate have the same hash of a known of something that you have already. So basically, hashes are used that if the contents have the same hash, they are assumed to be identical. And this is exactly why you store the hash and not the password, not the password itself. And you can validate content integrity. And for example, you can index files, which is the common place where you can abuse hash collisions. Like if you index PNG with hash collisions, then you are at risk. With sorry, if you index PNG with MD5s, then you are at risk of such a risk, such a like you could be some stuff could be stolen, some stuff could be hidden and whatever. Especially with PNG, may mean that critical, unless it's a of course very critical document. Who knows? But with malware, much more important. And if there is a hash collision, then yeah, this is a very weak collision here. This is a very weak hash here, and you could generate two contents that have exactly the same hash. But again, that's very unusual for a cryptographic hash such as MD5 and SHA-1 that have a huge uh, amount of bits and are proved secure so far, So a common confusion is that hash collision is not password cracking. Password cracking is about finds a string, a password that matches a given value, and hash collisions is made two different contents, most likely one good and one bad, with the same hash and with some extent of control over these two content if possible. So again, it's impossible to generate to find the content of a file with a predetermined hash such as MD5 or SHA-1. Some hashes were broken in the past, but even there, they were broken theoretically. They were one of those two. I don't remember which one was like, oh, you can, if you do this kind of operation X time, then you can get one bit. So basically, if you do this crazy amount of time, then you can actually have this attack. It was proved, but not actually done in the wild. And I think even MD5 and MD2 don't have a pretty image attack. They are proved broken, weak, but and therefore there's no extra research to do this kind of pre-image attack. So what we can do with hash collisions is that to generate two or more different files that eventually will have the same hash. You don't control the hash, the final hash, but the content will be different, and you can know to some extent what are the differences uh, between the two different files. And with some file tricks, and so, for some given file types, you can instantly generate files that run there the same ways. It's not necessarily uh, it's not necessarily possible on every file format. Okay, I can't I can't imagine how it would work in that order. Okay, I'm not sure. Hi, Jilal. I'm not sure what you're referring to. Okay, so in the core Kami GitHub repository, you will find you will find can't imagine. Oh, sorry, it's 18 folder in the bookmark toolbar. How where do you keep your porn? Ha ha ha. You want a ban? uh 18 folder? No, the 18 folder is about the streams. Um So you have a lot of how so let's what did I want to say? I'm stuck now. So yes, basically all these kind of examples here. You have Mark Stevens and I with the JPEG having the same hash files, and those files are all colliding. They also have the same MD5, even though they're most very different. And I provide also the script to reproduce these tricks, but also with pre-computed headers, so that you don't need to compute anything. So it covers a lot of file formats, not all of them, but yeah, that's you will see. So is it about just new collisions? No, it's not. The trick is that now with I will zoom maybe. Now the trick is that with some accelerations you can actually have stuff. You don't the computations are already the collisions are already pre-computed. Therefore, you can just reuse that to generate instantly two colliding files with arbitrary content. So this is in the idea, and this was the idea between Shattered. Mark Stevens wanted that we hack. So basically, the prefix that we computed was reusable for any file format. So basically, regenerating this file was very light, only takes a second or something. But the prefix is the very difficult part to compute. We'll see what it means. Okay, so uh, yeah, let's see. So again, hash collisions are usually perceived to apply only to a pair of files of the same file type. This is actually not true at all. You can have a lot more files. We did a few examples, uh, and of the same file type. No, you can do collisions across several files, and even more than two, and a lot more. And colliding files are expected to be very different, but for Shattered you can see that they can be very, once you control everything in the output, then you can actually you can control two very different things, or just a tiny bit of difference. You control everything. So for example, for the Poker GTFO 19, I did an instant generic PDF, PE, PNG, MP4 collision. So 4 file types, and reusable, and used in the actual output of the PDF, which was generated by LaTeX. So very definitely not a standard. I made this thing to show that yes, it can be a lot more than 2 files, and very similar, or like here you really have control about stuff you do. Um, and hash coins are just more complex. May hopefully we'll cover it to later today. Hash coins is how can I say? Um, Yeah, it's basically adding a lot of hash collisions. This one has 609 hash collisions to be able for the file to display the actual output hash in the on the homepage of on the front page of the paper. And it is actually a Nintendo Polyglot, and Nintendo Polyglot also does the same, showing the hash of the file. It's the same file, right? It's a PDF and an NES-ROM, and they both show the hash of the actual file, the MD5 of the actual file. And for example, I reused the Shattered prefix here. That's the Shattered file, and I reused that to do in Poker GTFO. Which one is it? 20 something, or I don't remember. 16 or 18, sorry. And this is this is basically the same PDF with the same SHA one, and you see that the image has changed in the front page. So don't be fooled. Shortcuts are necessary. It's not that you can hack all kinds of files. And for example, these files are actually very difficult. I mean, don't have shortcuts for easy tricks for reusable collisions. And this is actually interesting because zip and tar are covered by my inside out presentation, but in a very specific uh, it's not actually zip, and it's not, I mean, it's not just any zip, and tar is not tar alone. But the good thing is that's why it was interesting, is that these tricks can be reusable for future collision attacks, most likely, for example, for SHA-2. Like, you will have the construct, because SHA-2 has a similar uh, structure, block logic using collision blocks like SHA-1. It would be very likely that these tricks will be reusable, which is exactly why I started doing a lot of these tricks for MD5, because actually, because MD5 is easy to compute, and so basically these tricks can be reused whenever SHA-1 collision becomes cheap. Cheap, easy, fast, and so on. So basically these tricks can be reused over all these. Mal SHA-1 is the one that I mentioned earlier in the SHA-1 backdooring exploitation. But where's my slides? And so basically you can reuse these tricks over this MD5, SHA-1, MD4, most likely, and so on, because they use the same constructor, the Merkel-Demgerd, or I'm not sure how you pronounce it. So the goals for this workshop, but we'll do more, is just to understand basics of file format structure and manipulation, and to understand a few hash collisions attacks and how they can be exploited, and then come up with your own exploit. So basically, the idea is that you index, you use study a system that indexes files with MD5. What can you do? And this is actually the logic behind the Inside Out paper. I was told that some agency is indexing Office files with MD5. What could be the risk? So no one uses MD5 anymore. This is a bit old, 2019. Like, which we learned that WeChat is actually using MD5s, but nowadays, even what's his name, Radius, the um, the protocol was only broken last year, and until a few before it was actually broken in place, it was like, hey, it's actually not broken, therefore the MD5 use of in Radius is safe. So basically, people in 2025 still believe, if it's using MD5 and it's not broken, then it must be secure. So it's sadly that it's still the same, but I mean, Radius being used everywhere, you can tell the problem. So that's the Shattered attack. Had a few awards, and best paper, Pony Award of cryptography, and there were a lot of slides of different aspects. Even Pierre, sorry for your name. Is the file still available? Pierre Cartman, yeah, Pierre Cartman presented on the slides aspect of the video, of the computation aspect of the SHA-1 collision. Mark Stevens presented on the crypto part. Yeah, so we really presented a few interesting aspects of this effort. That was a very interesting thing. So basically, hashes are safe if, once you do check if contents have changed, then you do nothing. But if I upload a clean file, you store the hash, and then you whitelist this hash because, okay, the file is clean. Then if I send a new file which has the same hash, if you store the new file with the same hash, then, and it's already pre-whitelisted, then it's a risk. Uh, it's a risk if you provide randomization for crypto keys, and if you control, again, a file in a file set, then that's going to be abused. Like, I can send you want a file from me, I send you a file, you index the MD5, and then I send you a file much later that will have the same MD5, that might be a very different file type. And if your system is automatically accepting the file because the MD5 is whitelisted, then you are at risk. And this is transparent. This is a cryptographic problem. This is not a weakness that can be fixed. I mean, the system has to be reworked. But again, it's not like some MD5 will not work and some won't. It's like, that's the good thing when you exploit cryptographic stuff. It's like, it works everywhere. The hash is everywhere. The hash are standard everywhere. So yeah, big risks. It's not a bug that can be patched easily. So exactly, collide a normal file with a malicious one, and you sometimes can do it in the fly, especially with all the scripts are generated. So with this workshop, you can come up with your own scripts, your own techniques for other file formats, and then so you a few hours of research and computation that would be enough. I mean, if you're just an individual for MD5, if you're government, maybe for SHA-1, and then you can craft something that will be reusable. So very important, I think, in general, is that people say, hey, you say MD5 is risky. Okay, now give them a picture of something nasty and a picture of the CEO, and it instantly has the same MD5. Then people will learn. I let files do the talking very often. Just provide the files rather than it's how you convince people. Like, oh, I index files by MD5. What's the risk? Hey, here's the risk. Check these two files. I can reproduce any pairs of file instantly. So NMD5 collisions are a good hacking challenge. It's like hacking a file format. Hacking a file format is reading being able to read the file format, manipulating and abusing parser. So it requires some understanding of the file format to an extent that the new file that you craft are working, which is a good way to make sure that your knowledge is good. And best example is that it gives undeniable proof. When you have instant collision on file formats, it's a pretty safe result. It's a pretty strong result that, hey, now I know this file format a bit. I know how it works a bit. And yeah, when cryptography is fine with it, when you have cryptographic properties that are okay, then yeah, it's a pretty strong statement. It's like, yeah, this is a good it's a good step of knowledge of a file format to be able to craft a hash collision. I should do more of them, but just that actually I have a lot better plans for hash collisions in general, but no spoilers. So it's pretty good. It's a pretty good result. But don't worry, I don't know anything about crypto. I'm totally not the best person for crypto. You don't need to understand cryptography or math. We'll just use existing attacks, and most of them were provided by Mark Stevens, actually. I will not cover FastColl here because it's too new and doesn't have so much impact. I mean, it's brilliant, but it's not about file formats that it has impact. So you don't have to be an expert on file formats. You just need to understand their overall structure. You don't need to know the whole beef cuts, but you just need to understand the basic knowledge that there is a header, there's the body, there's the tail, and so on. And just this that you can see from my file formats posters is even too complex. You just need to understand that the high level structure, that for example a PNG is made with chunks, and that's all. So that's all you need to know. And because we just ignore the content of the chunks, we'll think in block, and we will align them like standard. And basically, we just work in blocks. And this is exactly why it's like playing a puzzle game, Colltris, which is why it's like playing puzzles with file formats. So now you just need to know the rules of each block, and this is exactly what we're going to go through. And yeah, if you don't want to go to the technical stuff, just check my Kill MD5 talk. But now let's dive. So you just need to know hexadecimal. You just need to know some basics of ASCII. And of course, NDNS. Yeah, no big surprise here, just the basics. One thing is important is that we will work with blocks of 40 bytes, or 40, yeah, exactly, 14 hex, so 64. So four rows of hexadecimal. This is very important because that's the size of the blocks in all these hash constructs. So don't be wrong by using a hex editor that doesn't wrap at a different length. This is important because the whole logic will be wrong. The way we will see, it's really a stack of blocks. So what are hash collisions in practice? It's computation that generates two distinct contents with the same hash. We can we can set the start of this content, and we'll see why. And a hash collision generates a lot of randomness, and the final hash is not known in advance. It's a reminder, and now let's see. So you need if you just want to go through the examples. But again, in the GitHub repository, you have workshops and you have already all the computed examples. And maybe even I created some. I remember creating some logs, animated logs of the computation if you want to simulate it. Anyway, and let's see, can I zoom? Yes, let's zoom back. So if you cannot compile and computation is too slow, well, just look at my prefixes and learn from it. You don't necessarily need to do it, and you can just run. FastColl, the software from Max Stevens, is very easy to run. So you just need some hex editor to train yourself if you want, and some hex editors, some hex tools, and this workshop and these slides. If you're not familiar with Kaitai, it's pretty good, and it has its online viewer that you can really learn. It has its own grammar. You can create your own grammar. Simplified grammar is a good thing, so that you don't need to parse the whole file. You just need to understand the overall level. And the problem with Kaitai is that it instantly fails on invalid files. So basically, this is what Kaitai looks like. And so basically, there is a hex viewer where you drop your file. It's not an editor. You have a YAML editor for the grammar, and you have here the result of the output. And you have a lot of grammars, but your grammars are stored. So now, if you're not familiar with file format manipulations, collision with the 2L colliding. Nice. Oh, because it's a ligature. If you're not familiar with the, it's weird, Vincent. I don't see your. I see your comment on a blog on a machine, but I don't see it on another machine. I don't know why. I don't see the other machine is not showing all the messages. It's funny. Okay, anyway. So if you're not familiar with file format manipulation, don't worry. You don't need to learn the whole file format. Just need to skim through the specs, get an idea of the high level structure, then look for possible structure to be abused, and that's about it. A bit like I did in my weird file live streams with Mitra. You don't need to learn all the details. You just need to move stuff around and see what works and how you can move, how you can make free extra space. And of course, look at the implementations, like in open source implementations, or checking for YAML grammars or for grammars is also a good thing to help you understand the file format without having to go through all the little details of a file of a given file format. Now just grab a differ. Okay, no big deal. And Radif for Madari is interesting because it has this very visual file Hashclash view mode that is pretty interesting. It's not dedicated to hash collision, but it's pretty nice. Because we'll see that hash collision blocks are typically at some point a lot of randomness with tiny differences in the middle. So this is why it's interesting to see suddenly where, oh, there's a difference, but it's just here. This byte is the different one. So let's try our first collision. And our first block in our game, the identical prefix collision, an IPC, FastColl. So, oh, there's a bug here. So collision computing is a very random process. Like the computing time can be very different, and you just don't know in advance. And there will be differences for result from each execution, which is why you need to plan the future structure of your file for a given format, even not knowing what the actual content of the collision will be. And sometimes, okay, that's a problem, but not with FastColl, but sometimes final result might not just collide. That was true in the past, and computation might be stalled. That was true in the past because now there's a colleague who implemented a better version of it that is preventing this problem. So that's stuff from the past that restart and backtracking might be required. Initially, Mark Stevens' tooling was extremely clunky and messy and very hard to use, and I was completely lost. And because of my numerous complaints, he eventually upgraded his tooling, thanks to him, to make it very useful. And nowadays, some collisions just git clone, compile, and run, and wait. This is like awesome compared to what the chaos that it was initially. And basically, as I've highlighted here, perform the steps below until collision block is found. It's not possible to say how long it will take. So it's a very random process, which is a bit unusual to most people dealing with file format manipulations and in general, So let's start. Mission start. And just running a FastColl on an empty file. You create an empty file and you just run FastColl and it will generate something. And maybe I can do it. So let's empty duck. Okay, empty text. Okay, and empty. Okay, and no, does that work? Yes. Okay, and yeah, does it work? FastColl. Duck. And there we go. And now we have two files, and these two files are different. Very tiny differences. You only see a few bits. So I moved the cursor just here and here and here. And it's, as you see, it's 2 blocks of 40. And you see that the patterns of difference is here. Sorry, I will remove the highlight now. So here, and it's repeated. The offset of differences are the same across the 2 blocks. So we don't know how long it would take. We don't know the actual result, but these 2 files will have the same hash. And these 2 files are different, but have the same hash. Woohoo, magic. From nothing, generate 2 files with the same hash. Oh, so I indeed provided the recording. So let's see if this recording still works. It would be interesting. So I cloned the repository, and the recording is in examples and the SVG. So that's a file FastColl. Let's see if it works actually. I mean, because the recordings were done with SVGs, like animated SVGs. Yeah. So basically, you don't even need to run it. You can just run the animation. So these examples are from the repository, and that you see that's the outcome of the output, and you see the differences. So I made it so that sometimes people were a bit afraid of actually running computation when I did the workshop, and that's how I did it. That's providing everything is on the repository. And also, again, I mentioned that you have in the workshop subdirectory of the repository. So workshop directory of the repository, you have all the computed prefixes so that you can learn already from. That's the one that are provided. Collisions, workshop prefixes, and you have the existing files that I provided in repository. If you want to learn by yourself without installing and compiling all the tooling, you can even simulate that it's recorded the execution of a recording. Okay, so I still wonder why I don't see the whole on my other machine. I don't see the log chat filter all messages. Oh, okay. Now I see everything. Okay, now I can see more easily what you put on the chat. But I'm glad I didn't ignore any message. Okay, so that's easy. And yeah, 2 blocks of 64 bits, totally random, with a few tiny differences, and the differences are in the same offsets and bits of each blocks. And it's twice the same pattern. Of course, your result will be different and very unlikely the same. So now you can just you rerun it, and suddenly you will see that once it's very fast, and this other time it's super long, and the output is different. That's okay. Completely different, still random looking, completely different from before. 37, 75, C1, and now it's a 1D 9256, completely different. Still random looking. Just ignore the ASCII because it doesn't make sense. And the differences are at the same offsets. So a hash collision is a bit, in this case, is a big pile of computed randomness with tiny differences. And the final hash is not known in advance. Difference is always the same offset, chosen specifically because of weaknesses in the hash function. And the interesting story is that for the first hash collision ever by Wang, if I recall, a Chinese researcher, a female researcher, it's because she said she slept on the specification of MD5 for many years, and she did with pen and paper. And one interesting thing that is not mentioned in these slides is that from one file, you can, in this case, generate the other one. And that's actually funny because for the shattered collision, I remember that Mark Stevens only gave me one file and say, hey, of course, he didn't say that, but like he knew that I could generate the other one. That was like, hey, oh, here is the collision. Here is one file. But actually, I believe that in the Hashcoin directory, there are tools to actually help you to generate to flip collisions, because it's actually interesting with Hashcoins. Okay, so I have battery. Yeah, I do have battery. Okay, so big pile of randomness with differences are always at the same offsets. So now you can add one prefix for both files, and this prefix will be used in both files. So here is a prefix with a few bytes. Okay, tac, let's do it. Let's go back to my directory. Where is it? Tac, tac. And let's run stuff again. Let's call empty is not empty anymore. And this time, 17 seconds, this time 0.6. And now, as you can see, S01 and W, I think it's different collision strategies, if I recall correctly. And now we have the two files with our prefix at the top. And you see that there is some rounding to the next block of 40 bytes, so 64 in decimal. And then the collision blocks are added. And the differences in collision blocks are still at the same offset. F4, 74, 26, A6, and so on. 75, F5, and so on. So basically, the prefix is common. It's an identical prefix collision. The prefixes are padded. The prefix is padded to the next boundary to align to the next 64 bytes. And then from that point, the collision blocks are computed and generated. The collision blocks depend on the value of the hash at this block boundary. So if you change a single bit in the before the content, then the starting value of the MD5 will be totally different. Therefore, collision blocks cannot be reused for even a single bit difference in the content. And there is no shortcut. Like, it's complete recomputation. It's not because you computed a lot of hash collisions that you can do a next one faster. It's always restarted, complete computation from the start. There is no resume. There is no resume. There is no resume just for the final from the starting files, or from the output of the computation, of a previous computation. So now you will see that here is a file with a few bytes. Is this what I typed? Yeah. So as you can see, mine is different, but here is a file with a few bytes, and yeah, I got the same result. Same result, but again, the differences, the collision blocks are different, and the difference are still at the same offset. You see that sometimes here you see that 2 bits are different, and here it's just 1 bit, but it's because it can be addition. So it depends if there's a carry or something. You see what I mean? But the difference is actually based on the words. So this is how you can. This is why the offset seems different, but it's just that it was added, but there was no carryover. So MD5 and SHA-1 are processing by blocks of 64 bytes. So now, because you have files at this point, you have the same hash for both files. Whatever you happen next, will give still two files with the same hash. So same prefix and an extra suffix, and that will be the file. The hash will keep constant across the two files despite the difference, no matter the suffix. And this goes top down, right? So the computation blocks depend on the prefix and is only working for a single hash value of the prefix, but a single hash value, which means you can chain them. And then you can append whatever you want as a suffix, a common suffix to both, and the hash will keep the same. The hash will change, but it will change the same way on both sides. So all current hash collisions work with such alignments, padding, adding at block boundaries and number of blocks. Well, to be honest, now it's a bit wrong because since last year, because of the latest attacks, the text call attack, brilliant stuff from Max Stevens. But still, from file format perspective, this is true. So every pair with the same hash will have the same length, and the end of the file is very identical because of the suffix, or very high entropy if there is no suffix, and this is just collision blocks. So we know this is why it's a block game. We always work with 64 bytes block. It's really a block game, and double check again your hex viewer wrapping. So congrats, you completed your first FastColl, and yeah, not everyone does that. So you can still simulate it by running it, the other file or the other FastColl. I added also FastColl with the prefix. Cat prefix. Here is a file with a few bytes. You run it, and then it computes. And then I hit my mic, and then the computation is done. So now there is a prefix that is optional, but is usually a good thing because otherwise the file starts with randomness. It defines the start of the file, but the prefix can have arbitrary length. Its content and size make no difference at all. It's just the value of this size that is important. And the prefix can be empty, and yeah. Then after that, there is some padding to 64 bytes. The content doesn't matter, only its length. If your prefix is aligned to 64 bytes, but there is no need for such a padding, of course. Hey, Iceman. And then there comes the collision blocks. We compute a pair of blocks full of randomness with tiny differences on each side. I mean, between the two sides. And despite the difference, the hash of both files will be the same. And these collision blocks only work for that exact prefix with the padding. I mean, again, you can consider the padding just the prefix being extended to a boundary of 64 bytes. And then you can optionally append anything to both sides, the same thing, and the hash value will remain the same. The two final files will be still having the same. Show us SHA-1 collision, says Iceman. Yeah, not yet, and definitely not computed on my machine. But yeah, let's start slowly first. Fast collisions. So this is an identical prefix collision. It takes a single input. The prefix and suffix will be identical. The file will be almost identical. The prefix is identical. The suffix is identical. And despite the randomness, the collision blocks will have only a few bytes of randomness. SHA-1 actually has a bit more. Can I show you SHA-1 collision? Show us SHA-1 collision, he said. So, okay, let's do examples. So let's go in workshop, GitHub collisions, workshop. And is there? That's the web page on all the collisions or the workshop page, So you have the fast collision with the prefix Unicoll, spoilers, and then you have the Hashclash and shattered. And you see that the differences in the case of shattered, here are SHA-1 collisions. So this was, if you remember, shattered PDF. So of course the prefix there was a single computation of shattered as far as I know. And it started declaring a PDF. And then the differences are like, I have these columns. This is interesting. And you see that, there's a lot of difference. I mean, the green is identical, of course, but you see columns of red of differences, very predictable manner. And the very interesting part is that the first byte of the hash collision is having a difference. So basically, this is the part that we exploited. The rest of the file, we don't care. We just base our hash collision on the first difference in the first byte of the collision. SHA-1 is used in Git. Is that a problem? That's a question from Vincent. Okay, SHA-1 is used in Git, but SHA-1 is not used. Okay, so that's actually interesting because when we released Shattered, it instantly broke Subversion worldwide because Subversion, if I recall correctly, it's Subversion. Because Subversion was using SHA-1 directly. And basically, whenever you would push the two colliding files with the different content on a server, on a Subversion server, then the Subversion servers would enter an infinite loop or something, a never-ending loop. Not an infinite loop, but it suddenly triggered the bug. So basically, it failed Subversion in a worldwide way. But Git is using SHA-1. You're right, but Git is not using SHA-1 on the final file. It's using SHA-1 on the Git object. For this case, I would recommend the very good papers from what's her name. I have the document here. What's her name? I'm sorry. Git object booklet. What's the name of this thing? Oh, I don't remember her name. But anyway, so Git objects is the hash of the previous object, some metadata, and the content of the file. So it's not just a technique. It's not just the actual file. So it's not that vulnerable. So basically, releasing the SHA-1 files for Shattered, just uploading its prefix to a Subversion, if I recall correctly again, server would have broken the server instantly. But Git is not vulnerable because Git is using not just the file content, but some other data before it. So basically, Git is not that vulnerable to SHA-1. I don't know if Git is still using SHA-1 actually. I think there was a project even at Google regarding is a Git using SHA-1 a problem? So that's SHA-1 collisions. And for the case of the newest hash collision, the Shambles one, you see that it's based on the same constrict, and you have again these big columns of differences. While for other hash collision like Hashclash, you have a lot of lines exactly identical. But in the case of Shattered, every line has some differences. But in the case of Shattered, we didn't care. Again, we just abused the first byte, and that's all. So that's for SHA-1 collision. I don't have any other SHA-1 collision to show. There are none others as far as I know. So again, IPC, so identical prefix hash collisions, have very tiny differences just in the collision block. The prefix and suffix should be identical. So what can we do with this? We can put whatever we want before and after the collision. We need the following. We need to have padding for alignments. There will be collision blocks with some randomness that needs to be ignored. There are some differences that need to be taken into account. And there will be we have to have some content that is put in the appended data. The problem is that with such a small difference, You typically need to declare, hey, I have an object, a file format object, and here is its length. And here in a single byte, it's very hard to, there are very few file formats that have something that is valid on a single byte that says, I declare something and here is my length. And if you saw my previous streams, we will see that the content is obviously GIF images. So properties of hash collision blocks, the start and end are aligned to 64 bytes via padding if needed. They are totally random, and there are tiny differences at fixed offset. We can change the offsets, and they depend on the hash functions and the attack. And these properties are common to all attacks on MD5 or SHA-1. Okay, so Vincent is adding that now Git is adding SHA-256. Not surprising. So FastColl is the properties of FastColl, 2 blocks, a few seconds, and the difference are in the middle, always from the away from the start and the end. Hard to exploit, the fastest, but the most limiting. In some cases, people like Mako and maybe David Buchanan added patch FastColl so that it's only giving a result with some given value. Like, okay, give me FastColl, but just force that the next byte has this kind of value to make it potentially good, a bit better. So what makes exploiting FastColl so difficult? Every collision difference is surrounded by random data. So you will not be able to know what's in advance or before. So it's usually impossible to declare a structure and its length in a single byte. And again, you can work around, of course, is that you have some external code that checks the difference. Another difference is, that's how I showed it for Poco GTF4. That's for GIF made by SPQ, if I recall correctly. He patched the difference so that it creates a few more filters on the code so that the computation takes a bit more time, tiny more time, but is still under the constraint of a FastColl, but just with a better output. So basics of most file formats. Most file formats will think very easily in block mentality. Again, very simple. There's a header required at the start of the file. It defines the file type, usually with signature, version, and metadata, and whatever. Then there is a body that comes after the header. And it's made of chunks, hunks. They have different names, segments, boxes, whatever, that frames that may be moved around under some constraint. And then there's a footer that follows the body. And the footer says that it indicates that the file is complete, and the parser ignores any following data, any appended data. And what is also important is that very often the footer is identical. There are a few footers like pickup that replicate some data that was, for example, before in the file, but very often the footer can be just constant onto all files. So the footer shows no problems of logic at all. And then there is very often what I call parasites, or you can command block. Again, this is simplified. Most formats accept a command block of some kind. Usually can contain anything, not just text, like whatever. It comes with it's usually, so it can contain anything. So it's perfect to skip collision blocks or to align stuff or for extra data. It can be inserted several times, so they are just entirely skipped. So they have a lot of use, and usually they are length defined, which makes them awesome. So you can, if you have to align the variable length with the collision block differences, and that's how you can end up having a command block of various length. A common mistake in file parsing, in file formats, a common misunderstanding is that robust parsers are detective. They just try to locate stuff. While most files are perfect and very aligned and whatever, most files have all you can move stuff around, and or you can, and until the end of file is reached, Then they check if there is everything they need, and that's all. So basically, most parsers are very robust. Most common parsers are very robust, as in they accept very, very weird files. They just look for the information, and if they are fine, then they render the file, and that's exactly what we abuse. So this is the image. Imagine you are served a portion of French fries that way, perfectly aligned and everything. That could make sense, but this is not usually. This is how a file is usually perfectly organized, but not French fries. And on the other hand, we will do file formats a bit like the usual French fries portion. So let me plug for some battery. Up. So most files are perfectly structured. They were generated by one of the standard libraries in normal conditions and with typical requirements, and no corner case. And again, we want to abuse detective parsers, so we move stuff around, and the parser will find them, and they will be happy. So basically, this is a very easy example of a header, a body, and a footer. And if we add one command or several commands, and we add appended data, then all these files are equivalent. Here we just add one command, and here you add a longer command, and here you add one command and another command and yet another command, and all those some appended data. These files are equivalent, are functionally equivalent, because they have the same header, the same body, and the same footer. And the comments are ignored by parsers. The appended data is ignored by parsers, and the number of commands is usually, and the length of the command is usually ignored, even though we changed some stuff with the alignment and we've made the file bigger. So if you take two file types of the same file, so if you take two files of the same file type, two header, slightly different, and two bodies of different length, and two footers, which usually are the same length, but they can be different still. Now you come up with a special common header that will somehow match both, if not all files of that format in some ways. So for example, in the case of PNG file, you have grayscale PNG, you have color PNG, you have transparency. So if you take an RGBA, so full colors and transparency file, any PNG can be converted to that. While on the other hand, grayscale is only matching a very small set of PNG. So basically, you come up with some header that matches at least the two files, and if not all the files of that file type. Now you put this collision, you put this header first, you put your padding, and you put your collision. Padding and randomness with tiny difference as usual, and and margin errors have to be mitigated. Sometimes it's tricky. Now let's try to come up with a super file that combines both files data. So after that, you append the two sets of body and footers from the two original files under this magic header, under the collision, and you will abuse the collision block difference, so that with one version of the file, it will find the first body and footer, the content of the original content of the first file, and with the other difference, the parser will somehow find and the second set of body and footer, which makes how can I say? Which makes and the rest is ignored because it was skipped over, and somehow this was integrated in the comments. You get the idea right now. And in the first case of the first file, because there's the footer, then the rest of the data of the second file is ignored. So now you have a super file that has two variants with differences. Same prefix with the magic header, the special header that is common to both files, the collision blocks with a difference, and you see that the suffix made of some content of the original two files is the same. So this is, and since it's an identical prefix collision, the hash value of these files is the same. So we don't know what file format we're talking about. We don't know exactly the construct, but we get an idea that we can now, if we have a header that works for most, if not all files of that format, that can work for all files of that format, then this computation is reusable. And then with arbitrary set of PNG or maybe JPEG, then you can reuse this instantly. And you just need to move data around. You just need to convert your data to this special header if required, some normalization. And then this will be uh, then you just need to do this transformation and append it, and these two files will render what you had on file A and what you had on file B, and yet require no specific cryptographic computation and is reusable. So it's like a ski slope with two special jump ramps, and there's here I made a fun to make you go faster and you land a bit farther in the file over a nasty area of collision blocks. It's at the time I was trying to do some comics. So each colliding file will render as one of the original pair. So now you had arbitrary content here. This file renders the same. And you have another arbitrary content here. And this file renders the same. And these two files have the same hash because of the IPC construct. So now let's look at a very special collision. The thing is, because FastColl is a bit tricky, I will not cover that right now. Let's do poetry. And we had this weird poem where what if we change the 10th letter of each sentence and we increase to the next letter? Cares to dares, have, gave to have. Thank you, English, for change of pronunciation. Shards to shares. What about it? What if we could change the 10th letter to the next letter? You can predict both content in a very easy way. That's our second block. It's a Unicoll, it's an IPC, but with some very different properties. So Unicoll is an IPC, so it requires on a prefix. It relies on a prefix. And maybe use exactly this prefix because Unicoll can be a bit picky with some prefix constraints. So just use it, and hopefully I have also the Unicoll so examples. So GitHub collisions, Kokami collisions, examples. And do we have the Unicoll? Yes, I do have Unicoll computation and as an SVG. So I don't even need to run it myself. If it runs, does it run? 6 minutes. So it takes a bit more. It's a bit cryptic. I will go faster, you know. And then at the end, you have the two files with the same collision. And I did a typo that will be stored forever. And now you have the difference. Here is my prefix was changed to here is mz prefix, which is a bit hard to pronounce. So here is my prefix was converted to. So, okay, sometimes Unicoll doesn't give you files with the same collision, then just rerun it. And now here is my prefix. The 10th letter was converted to the next letter, mz prefix. So this is very interesting because we can know what we want on one side and we can know what we want on the other side. It's a single prefix where we will know the differences. So, and you'll see that now the prefix is a part of the collision block. So actually we just forced collision block inside the prefix, inside we forced the prefix inside the collision block. And now we have some predicted content, but we can also predict the difference. And you see again, there is a second block and there is a difference again on the same offset of the block. And this time it's +1 and this time it's -1, the opposite as usual. But this is very predictable on the top. So it's a This is why it's called Unicoll. It's a kind of unicorn of a collision. It's a hybrid IPC where you can define some data around the first difference, and you can set the first difference, and no other collision does that. So it's super predictable. Now, when I did this workshop, some people were like, "Hey, I'm just going to put the difference where I want," and this is not exactly how cryptography is working, how MD5. So no, you can't. You can change it as you like. There are other working cases that are absolutely not easy to exploit. And actually, Mark Stevens implemented two other Unicoll with different parameters. With n equal to, you have a very difference. The difference is not +1, -1, not as sexy, but you can have you can have a lot more data. You have a lot more data after the phase difference. See what I mean? You have, the difference is earlier in the file, which can be interesting. And with Unicoll n equal 3, so n1 and 2 and 3 are corresponding to these parameters in the Unicoll script, which is corresponding to this stuff in Mark Stevens thesis. And for Unicoll 3, the interesting thing is that the difference is on the last byte, which is a bit unusual, which could give you power, because then you could exploit this with something in the suffix, maybe. So now if you put another prefix, well, the prefix will be working as usual, will be kept as is, and the rest, Unicoll will do its magic on the boundaries, Only the last block is integrated in the collision, no padding in the case of Unicoll. So now the good thing is that this gives us a lot of power, Another thing is that the length of the second rule of last prefix blocks, the last prefix. So the last prefix, because again, the earlier blocks of the prefix will be, let's just put it as a standard prefix. But the last block in the prefix needs to follow. They have a length of multiple of 4, because otherwise it will not work. And then if the longer the part, here is my prefix. If you put this part longer, then it might work, or it might take a lot of time. So in the case of the standard version, 2 minutes for 24 bytes of control. In the case of you just want 4 more bytes, 13 minutes. So you see, it's very different. So Unicoll is a bit different, but adds 2 blocks after the collision. I mean, after, you see what I mean. It takes a few minutes. It doesn't take a few seconds, but the difference is in prefix. So slightly slower, but easy to exploit. And now you see why the block has a different shape, because of that difference that pokes out of the block, and you have control before and after that difference, and you know the value on two sides of the file. So now let's exploit this. You want to plan your exploit, so you need to study the format specs, look for features that you need in a file format, and then you choose: is it good for FastColl? Is it good for Unicoll? You plan your file structure, and this is exactly what I suggest, that you plan a mockup file really from the beginning and before the computation. But you check if the file will work in both cases, and you try with a few, initially with one version of the file difference, then you randomize it with the script, and then maybe you're ready for the collision. Because again, for the shattered thing, it took a lot of computing, so that was a lot of pressure that you provide a working script, a working prefix, that no matter the output of the computation would be valid, would be able to produce valid pairs of files in a generic way. So then you craft mockup files to make sure everything is fine. You ignore collision range, so here full of 1, 2, 3s, just to remember where you are in the file. Then you extract the prefix for your mockup, the exact prefix, and then you run your computation. So what makes exploiting Unicoll so easy? The first difference is surrounded by chosen text. So no restriction to declare something after or before. It's very flexible, and the difference is +1, which is super trivial to impact. So to plan. So basically, one chunk, for example, will be exactly 100 bytes longer. And if you remember, that's 2 blocks of collisions, which is less than this. So perfect, not too big. It won't grow to be to be suddenly uh, gigabytes of differences of bigger length, but it will be very easy to plan and not too much. So really good, because some collisions would be possible, but suddenly you need to create a 2 gigabyte file because the length is I don't know, big endian. So the layout of a classic collision format exploit is you have one command to align stuff properly, and then you declare another command, and the length of this command will be exactly matching the difference in the collision blocks, so that the length of the collision block of the length of this extra command will grow differently depending on the version of the file. And then you put some data here, the data of your first file and the data of your next file. And this data is enough to render the first file, and the data that comes next is enough to render the second file. And if the command is growing, is in a big version, then the content of the first file will be ignored, and therefore the content of the second file will be the one being rendered. So in case A, the chunk A will be visible, and that will be enough for the rendering of the whole file. So chunks B will be ignored. And in the long command version, the command is covering the chunks of the file A, and this will be, and then the chunks of file B are the one being parsed and therefore rendered. So plan your generic exploit. Getting an exploit is a great to convince and test. Make a script to instantly generate proof of concept is better. It's very important to plan your exploit, but also study the landscape, because you may abuse some stuff that is not universally supported everywhere. Like when we try to exploit SHA-1 files, we wanted to abuse a feature that was definitely not standard in all the files. I think this is covered in our exploitation hash collisions. Maybe there will be an example. Yeah, this. We try to abuse color before for the shattered file. We try to abuse some color space graphical state thing to change the coloring of the content of the file. So it's a PDF feature, but it was not very well supported. So under Adobe, it was giving. So basically, you would see some text or not, but then under some other viewers at the time, it was not reliable. And which is why we ended up using this. The only difference in these two files are identical, except that the image they render is different. So basically, this is a JPEG exploit in a PDF, because the JPEG support compatibility across PDF viewers is very good, and the same tricks would work across all the viewers. We really extensively test that to make sure that this file was working. On this collision, the two weird files were working on all platforms. So understanding compatibility is important. Now, the problem with that is that you don't know the length of all these chunks in advance, which can be tricky. So instead, you do one extra command to jump over the command declaration. And basically, the variable command is just acting as a switch to cover or not an extra command declaration. And the advantage of that is that you can add this command later. This is part of the suffix after the computation, depending on the size of what you want to cover. So to make this fully generic. So now you have a chain of 3 commands. One for padding, to put stuff at 64 bytes. Then a command that will just add as an disable the next command or do nothing. It's a NOP or if just ignore next command declaration. Then you have this big command declaration that depends on the size of the chunks from the first file. And that's now this is generic. And you see that it's basically reusing the same technique, but basically these collisions, this is making it more generic. And the length of that command was known because it's just to hide the next declaration of a command. So you have to make sure that you can, depending on all the file formats, you can reliably know to which extent you will need to cover. So how big this will be to cover all the cases. So for some file formats, it's very easy. For some, it's pretty tricky. And merging PDF file pages or GIF frames is actually, so you merge two commands is a very nice way to normalize the two content to the same file, because basically the two documents contain, one document contain the two contents of the two files, and then you hide selectively. So now let's exploit PNG with Unicoll. So PNG is extremely simple and very elegant, most regular of the common file format. A signature, then a sequence of chunk. And yeah, maybe I shouldn't say PNG, but ping. But yeah, PNG, it is. There is a signature out of set 0. It has to be there, no problem. And then there is a chunk structure of a length, a type, some data, and a CRC. The CRC is no problem to recompute once you have the type and the data. And the CRC can be ignored in most chunks, but you can compute them anyway. And the good thing is that you can lowercase type chunk ignore. So if you have image header, you can if you have standard chunks that are in full uppercase that are super important, and whatever you want, Ange, Mark, Aling, Scroll, Skip, Jump, will be ignored if the first letter is lowercase. So let's walk through a simple PNG file, not the whole of it, just at block level. It has a signature, then a sequence of chunk. Starts with the length and type, CRC, and ends with the CRC. There's the data of the chunk in the middle. So now we see there is, to walk through a PNG, you check the signature, then you check for something that has random looking bytes, the CRC of the previous chunk, Indian length, so for something like, again, mostly zeros beginning, and then 4 bytes alphanumeric string. Now the chunk type, which is important, and skip the length, and just, so basically you can just visually walk through a PNG yourself by using this trick. Now let's just display the same file, but with skipping the whole range of the image data, because the rest is just header and a palette. And this, again, a sequence of chunks. Now it's very easy to implement, to manipulate. It's like chunks basically, and a signature. And you can add your own. You can add your own chunks as long as the first letter is lowercase. Now we need to add 3 chunks. It's very easy. But we need to align stuff. Okay, no big deal. You just need to plan. And then you can copy the whole image content after the signature. Yeah, because you take a PNG, you remove signature. This is a sequence of chunk. You just append the chunks. That's done. So you want to add an alignment chunk. and you want to add a collision chunk with the content of the file. So you see you added the chunks. Inserting chunks, because they start with a lowercase letter, will keep the PNG valid. And now we need to jump over the first image data. And this way, by doing this, we have the 10th byte that is on the length of the collision chunk, which so far has a length of 71. And we know that because there is 00 here, the difference of the other file will be 171, because big length in PNGs are big endian. So in one case, we will jump 71 bytes further, and in the other case of the collision, we will jump 171 further. In between, we can just add another chunk declaration. We have 100 bytes to declare another comment. And in the case of the file I provided, well, I even added a ASCII art because you have the room for it. So if you need to explore it yourself, you can use Kaitai. And again, you don't need to explore the whole PNG data like Kaitai. You just can explore a very simplified grammar for Kaitai, which will make it even easier. You will just see the file as chunk. So it's important to know the landscape. All PNG viewers seems to ignore the CRCs, at least not in the header. They start with the dummy chunk, even though the specs say that the dummy chunk, the first chunk, should be the image header. But OS X, Apple PNG viewers enforce an image header chunk because they support the other very specific Apple PNG, which start with the CGBI. So core graphics, a bitmap, which is specific to Apple. So basically, you need to know you know that by putting a chunk, a non-image header chunk, this will work on most viewers, but not Apple ones. But you know that this trick with Unicoll will still be working, but less generic, because the image header contains things like the file dimensions, the image dimension, the color space. So this will be less generic. This will be specific to some dimensions and some version. I mean, a standard, like the color space, the dimension, the filters and whatever. This will be specific to that file. So if you want image header first and then your collision blocks, then your collision block will be depending on this exact content of this image header. So congrats, reusable PNG via Unicoll. Correct CRCs in Unicoll PNG. So yes, CRC ignored. The collision blocks have different content, but you just need to compute the CRCs in Cascade. That's all. That's not very difficult. Chosen prefix. So now we have two collisions that are identical prefix. And so both takes 2 blocks takes 2 blocks of collision blocks. So 2 times 64 bytes. One takes a few seconds, but the difference are in the middle. Very hard to abuse. And the other has 2 blocks, but takes a few minutes, but the difference is in prefix and predictable. So definitely not the same power, but not the same computing time. IPC's limitations is that some formats have hard-coded offsets. You can abuse alignments, and you don't tolerate early comments. So basically, you need some data before anything that is abusable. Same prefix means same file type. Like if the 2 files start with the same exact bytes, then very often you're bound to the same file type. And if it's the same header, then most likely same metadata. You don't have a lot of flexibility because the prefix is identical. And sometimes the checksums prevent validity because you will have some difference, and then you cannot have a common checksum for both. So basically, you can only manipulate one level of current structure, one on the length of the current structure, not of a further structure level. It's restrictive. Now, chosen prefix collisions, Hashclash CPC, but it's called Hashclash CPC. But in the end, the repo is Hashclash, so I'll call it Hashclash. So now we have a very different block. Chosen prefix hash collisions. Let's see. So it takes longer and it requires backtracking, but now it's automated. Thanks for I forgot his name, who the one implementing that. That was great. It was actually someone who attended my workshop, this workshop, and he was fed up of having to deal with the backtracking. The backtracking had the good thing that you could do it faster, but he added the auto detection for that. It was not as fast potentially, but at least it was run and leave and wait. So in for Hashclash, you have variable amount of collision blocks, but the fewer the collision blocks, the longer to compute. And I again did I provide a Hashclash collision block? No, I didn't. Okay. Hashclash master of backtracking. So to launch a Hashclash computation, it's very easy. And nowadays, it's like there's a detecting stuff and it's doing stuff immediately. Very, very nice. Now you need two prefixes. And the prefix, we'll see, have a very different role. So here is a 9-block CPC of, I just put yes, and I just put no. So you see it's not identical prefix. And it added 9 blocks of different content with tiny differences in the blocks, in each block at variable offset. But no matter the content of the initial prefix, at the end you have two things with the same hash value. Any pair of files. You have two files, any pair of files, we can see them as prefix. The padding will be some difference. There will be some padding to the same length and minus a few bytes, 12. And the padding content doesn't matter again. But you need some space that will be used for randomization of the process. Random buffer, partial birthday attack bits. Now we compute a collision that will append different blocks to both files. But at least if the two formats, file 1 and file 2, tolerate appended data, this file will be having the same hash. And if they tolerate appended data, then this file will be valid. So now you know that hash collision is a very easy process. You have two files. You run the computation. It's done. That's all. It takes longer. And the difference are irrelevant because the difference could be in the prefix. Whatever in the prefix. The length of the prefix has no difference whatsoever. There will be some padding to the common length. And again, the two files, the two final files will have the same length. So their content and length don't matter. Shorter prefix don't make anything faster. And both are padded to the same size. There will be some space that will be used for the collision block. And then the collision blocks are added. By default, 9 of them. You can put less. It will take longer computation. There are 2 steps for a CPC, for a chosen prefix collision. And the first step is taking advantage of the GPU, but not the second one. Okay. So Mark Stevens created a computation that was only using do I have them? Prefixes, FastColl. No. Where is it? Examples, free. Where is it? Pop. Bin, maybe. Single CPC. Yeah, that's it. It's in the GitHub collision examples, and I stored a few historical CPC, a few historical um, collisions. So this one took 400,000 hours of computation and you see that it's a CPC, so MD5, and it's only using a single collision block. Pretty impressive, but this is not something you can do at home. And he also did an IPC on single block. Oh, okay. Let's see. Collision on a single block for an IPC. So here the prefix is empty. Not something that you can usually compute yourself, and not very important anyway, usually. So the impact is that of a CPC is that two file formatter append the data, compute the collision, done. Straightforward, but only works for a single pair. So totally not generic at all. Now let's see. We have this identical prefix and we have the chosen prefix, two different prefixes, and either prefix only exists in one side of the file, in one side of the collision. The IPC you have in the IPC you have both content in each file. You might leak your payload. In the CPC, you have one content per file, so the evil payload is not visible in the good file from a content perspective. Now, from file perspective, this is a deeply modified file structure with header to payloads and whatever. And from the CPC perspective, the file starts exactly like before, no change, and then just append the data. For an IPC, you can reuse pre-computed collision. So instant collision can be possible. But for a CPC, you can you have no reusability for different prefix. You need to recompute whenever there is any single difference in either of your prefix. Now, what about combining the CPC flexibility with IPC reusability? And you see the constraint, the monster that is a constraint. Remember that we need a special magic header in the case of the IPC, generic IPC. Now, using a CPC as a prefix like an IPC, more computing than IPC, so it's still the computation of a CPC, but then you have the generic aspects, instant reusability of an IPC. And instead, you can do a CPC with different headers, and then you end up appending the body footers of the two files. So you can mix valid and invalid files, or you can do collisions over different file types, for example. So let's do P collisions via a CPC used like an IPC. So that's a simple P file, a Windows executable. And Windows executable have this structure where there is a DOS header, which declares the executable with the MZ signature at offset 0. Then at offset 3C, you have a pointer to the further P header. And the P header is the thing that is basically the whole header of the P, declaring the sections and everything. And it starts with the P signature. Over it, there is the old DOS stub that is not important anymore. And there is sometimes this thing called the rich header because it has the rich magic in the file. This is not. You can remove those. The file will still be valid. And in the P header, there is the table section, which is the thing that says, hey, map this byte of the file to this address in memory. So basically, if you move the sections around, you have to update this table section. So when a Windows executable file is parsed, the MZ signature is found. There's the pointer at offset 3C. Do I have a P header here? Okay, let me parse it. And this section table is telling how to use the rest of the file. Now, as we said, the rest is irrelevant. These two headers can be removed. The P header can be removed. It's just a pointer. And whatever, if you want to move the sections further, then you can. And that gives you extra space. You just need to update the P section. Now, what about we do the DOS header is generic. And now we put two P headers at arbitrary offsets, but usually we know the maximum size of a P header. And we put all the sections of both files together. So I did this with two papers, please, executable and return to Obradin, binaries, and mecha, the SMS Sega Master System emulator from Omar Cornu, and his Wonder Boy executable. So you could collide two versions of Wonder Boy, and you could collide two Luke Pop, I don't remember, binaries. Well, whatever. You get the idea. Now, you put the two P headers in the same file. They both have sections, and you put the two sets of section in the file, and the two P headers will find their own section in the file. And the only thing that is generic is the DOS header and the pointers will be the prefix. The rest is not important. Of course, if you want alignment, then you can put some ASCII art, and then you have your collision blocks, your Hashclash collision blocks of a given length. So now you have reusable and instant P collision without recomputation once you did this. CPC IPC exploitation for P files. You can have two DOS headers with none of difference. No problem. Then you compute the CPC and you copy the P header. You open the section, you adjust the section offsets in the section table, and you have reusable instant collision with no code modification. You can collide WannaCry and your favorite game. The code will be visible in both sides, but will not be executed. Pretty scary. Now, of course, you can chain collisions, because what is important for a prefix is the value of the hash, not the content of the prefix, actually. So you can chain collisions, chain like a tree. Now you can the top nodes can be an IPC, other CPCs, or Unicoll, and you can collide more than two files. And n collisions makes n+1 contents collide. Sorry. So Mark Stevens did that. He said he collided all the pictures of the US president candidate, including I did Paris Hilton and a hidden one, 11 hash clashes for 12 PDFs. So basically, he could say, hey, I know the hash of the file of the next US president, even though we didn't know which one was elected. As I mentioned, I did that for 4 file types. And I did that collision trees, 8 Unicolls to change the content of each of the bytes. Remember this poem from earlier. So now, let's talk about SHA-1. SHA-1 has 2 blocks. Shattered is 2 blocks. We saw it earlier. So examples, workshop, prefixes, shattered, that's shattered, and that's shattered. That's my 2 prefixes of shattered. So do you see the prefix PDF declaration? Let's view it with everything, every element in the stream object declaration parameters being referenced further in the file. A tiny string SHA-1 is dead, which also provides alignment. And now, if you're familiar with JPEG, so there is a stream declaration here, the stream declaration of the object. Then immediately start with FFD8, the magic of a JPEG image. then FFFE, the declaration of a command segment in a JPEG with a length on 2 bytes. So now we jump 2 bytes further. So this is ignored in the first command that is here for alignment. Okay, and now we arrive to another FFFE, so another command segment declaration. And now we declare 1. Also, in the case of JPEG, the length is big endian, so this is 24. And here I declare 1, so that the length is long enough, and then came the difference of the collision block, and we know that the collision blocks had the difference in the first byte. So it's, in one case it's 173, and in one case it's 170F. So now we know that some length of comment will be different, and the difference between 73 and 70F is long enough so that we can declare another comment in the meantime, because declaring a comment in JPEG only takes 4 bytes, FFFE and a length. So within the difference, because we know the mask of the difference, we know that the length we know that we will be able to cover another difference. You remember that will itself cover more of the file. And Shambles is using 9 blocks. It's a CPC, but it's pretty expensive. Both are expensive. And again, it's a CPC, so the difference is not relevant. But at least we know that we can plan the collision with we can plan the collision with the easier collision. We can plan the properties, which is good. So shattered is an IPC for SHA-1, computed only once as far as I know. And the difference at start and end, which makes it easy to exploit. 2 blocks, 6,000 years of computation. And the difference are at start and end. They are columns, as we saw, but at least they are very easy to exploit. And here is the shutter layout, as I just showed you. And you see then that we jump further or a bit sooner. And then we can declare, because it's the fact suffix, a comment that will jump over other commands. And then we change commands to ignore some data. So now some file types have length type value, the length first, and some file types have the type first, which makes it harder to exploit. I mean, it depends. What is important is when you have the value, so the data, and you have the length just before it. So basically, you declare a jump over garbage data. This is a collision block. This is a jump. Ignore the collision block. And if instead you have to put a type, then you had to modify the length with collision blocks, but then you have the randomness of the collision blocks, which prevents you to declare a type. Okay, more details about shattered exploitation. And Shamble is a bit similar to shattered in the differences. And it's how do you say? It is a CPC is for SHA-1. I imagine, and the official proof of concept was about PGP stuff. So now let's wrap up all the known implemented attacks on MD5, which you can all run on a normal machine nowadays. And yeah, that's funny because this is completely outdated, because now Mark Stevens created text collision last year, which is totally breaking these assumptions. But the thing is, with all these already, it's powerful enough to cover most file format, and ASCII only file format. ASCII only hash collision is not that useful for file formats. Okay, the discussion here. On history attacks, that's the thing, right? MD5 is already considered dead for good for academics since 2008. So it's like, why would someone research any new attack on MD5? This is a recap of the different patterns of exploitation of different kinds of collision: reusable CPC, reusable IPC, and how you exploit the the usual layout that I said, with 3 commands for padding, length, and the extra command that is specific to the first file that you want to abuse. So now MD5 is a toy function. We certainly had fun. Mako implemented an MD5 collider on a Mega Drive, which is a much older. This is a machine that is older than MD5 itself. But it runs. It takes 2 hours. But you can run a FastColl. This is FastColl implemented on Mega Drive. Now, let's look at how we can abuse PDF. So you merge documents and you split the kids, which is the array referencing the pages of a document, in 2 parts. So basically to show 2 sets of page separately. And then you declare a catalog that has, so again, I provide the files, I provide the script and everything. So let's go examples, PDF, collision 1, collision 2, collision 2, where is my collision PDF? There you go. And you see, if you've seen my other streams, I added type catalog. Type catalog is a standard declaration. And now I added a fake MD5 is really dead now __ key values in the dictionary to align stuff properly. So that now we have the pages declaration. And this is a character in the Unicoll collision blocks. And we close the objects. And then in the case of object 2, so now we finish the collision here. And now we have 2 objects, 2 and 3, which refer to different how can I say, sets of pages in the document. So basically the 2 documents, this is the meltdown paper, and this is not loading. Hello, it's not loading. Why is it not loading? What's wrong, system? Oh yeah, Spectre. So these 2 files have the same hash, and actually it's a document that was created with all the pages merged, and then even individual arrays for each set of objects for each set of pages was referenced. And then the collision is working. The Unicoll is abusing this reference number to see 2 different pages, 2 different pages array. I mean, objects containing the pages array. Now, if we look at another file type, let's go through a few other file types. So PNG. So this is a PNG with these. It doesn't start with image header. So an alignment block. Oh, maybe I should take something to drink or whatever. So you have a chunk with the underscore image, underscore letter, saying that it's not important. And then you have a length of 33. And then we jump over this. So we know that all this MD5 is really dead now. Collision blocks, and then comes the alignment. Then comes the collision block, and the length is here. I mean, the byte that will be abused by Unicoll is here, the length being 71, so that you just jump over the collision blocks to some given length. And if we go to the other file, collision2.png, we see that this byte has changed 0 to 1, and the length is different. Now, just after the blocks, the collision blocks, we have the CRC of the collision block, then a skip comment containing some art. We have 100 bytes of freedom, and then we have the image header of the first image. But again, as you can imagine, the collision blocks are here. So this is the suffix that can be, this is the prefix and the collision blocks. This is a collision block. I mean, not here. The difference here is here. So this is a collision block because it's Unicoll. So all this part here was set as a prefix for Unicoll, but it's not an exact, you know how Unicoll works now. And the difference will be here. And then this is generic. In the case of JPEG, let's see JPEG. JPEG is easier. What did I do for JPEG? Oh, a picture of Mark Stevens and a picture of me presenting on both on hash collisions. So FFD8, as I mentioned before, that's the length of the. Oh, interesting. We can use. I forgot about that. JPEG is so flexible that we can use directly in the first collision block of the first Unicoll. So FFD8, that's the signature. FFFE, that's a declaration of a command. Here is the length. The command is extremely short, only 3 bytes. So that we declare, and the length is here. So basically the extra data is 1 byte, AA, probably for Ange Albertini, totally a coincidence. Then FFFE, another declaration of command. And here we have the difference on the 10th byte. So basically this is the prefix to put in our Unicoll. And we see that the length has again changed from 77 to 177. And then the same logic. What else do we have? MP4. Oh, let's go. Let's quit Hue. MP4. MP4. It's not a format that I covered. Collision 2.mp4. Very similar stuff. The chunks, the free. So in this case, it's the length is first, then there is a type. So the length, and if I recall correctly, the length is already, everything is included. And now we have the alignment perfectly. And thanks to Unicoll, 0179, you see 70s is around, because again, the 2 blocks are a bit less than 80 because it's Unicoll. So basically around 70s, then you declare the free chunk. The type has to be there, but in the case of Unicoll, it's possible to put the type after the length, and we jump over it, over this, over the collision blocks without any restriction. This is now the suffix, and we can put whatever we want. So we will have a new declaration of a length and a free. It's not called chunk. It's called box, an atom, if I recall correctly. It's called an atom. And here you have another atom. You see the same logic again, and then you have the actual content of the MP4 file. JPEG, as I mentioned, 127 to 177 MP4. Okay. Oh yeah, in MP4, I didn't mention that you have to adjust absolute offsets. So probably in the script directory, MP4, there is an ugly script that I wrote long ago. Is it even Python 2? It's not Python 2. And in the case of MP4, you need to there are some absolute offsets table in the MP4 file, and you need to adjust them. The so standard sample table chunk offset table. So you need to adjust the offsets when you relocate stuff. That's all. So the script is there. You can take arbitrary MP4 of the same dimension, maybe. So some files are not easy to abuse. I think I will stop today with this. It's already many hours. How long did I present? Where is it written? Where do I know? It's almost 11, so that's 2 hours of stream. That's a bit too long for one go. So I will stop today. No hash coins and stuff. I think I will do it tomorrow. The hash coins and advanced collisions and detecting collisions. I will do that tomorrow. I mean, the next stream. So some formats are not easy to abuse. And now, indeed, let's abuse exploit FastColl. Let's finish with that. Seems hard, but this is not necessarily impossible. It's finding the right file format, aka aligning planets. And FastColl is good if you have, but you only have a single byte difference and you have no controllable values around the differences. So very difficult to abuse with standard file format that require, as we saw, length, chunk types, sometimes even CRCs and so on, You couldn't have a CRC before that length because there is the randomness before it. So GIF is good for that because, okay, so the restriction for GIF is like instant computation. So this time we can actually use the GIF, FastColl directly because FastColl is so fast to compute. And basically we will trick GIF. It contains 2 frames, and the first frame is just displayed for the maximum amount of time, which is 10 minutes. So basically the 2 files will be visible. Collision, okay. Collision GIF. This, and actually if we went 10 minutes, the file will be visible, and that's the other file. So you see it's GIF, so it doesn't have a lot of some colors are lost, but it's okay, it works. Okay. And GIF, there is this weird file format that are punctuations, and the frame can be made of several images. The header contains the file palette and dimensions. The palette is important because that could be a problem. The palette can be at different places in the file. And commands are only in the extension, not in the header. So you cannot put the commands that would cover collision block cannot be put before headers. So there is no generic files collision for all GIF. You cannot put the collision blocks before the header. There's no way to do that because of that structure. Now, the header is dimensions and optional global palette. Then there is sequence of optional extensions and image data, and commands are here and extensions. And both the image data, the actual pixels, and the extensions, which means, for example, the commands, use the same subblock structure. So now the local palette can be a problem. So instead, let's just use okay, no, that's okay. That's okay. Local palette. Okay. So let's see the length. The header is 7 bytes, and then there is an optional global palette that can be variable length. You need to plan in advance. Then the extension can have stuff that define the delay between frames, which is useful when we want to put a 10-minute delay for the first frame, and the comments, and some stuff like looping, but we don't care. Then there is this 10 bytes restriction for the descriptor, just 10 byte size for the descriptor of an image. Then image, the palette has the image, an image itself can have its own palette again. Each frame can have its own palette. Now, there is very important, we will abuse this subblock structure. And subblock structure is chunking of the data, is chunked in small, the whole command, the whole pixels, the whole whatever will be chunked into smaller subblocks of 255 bytes max. And every of these little subblocks will start with the length. So basically, if we want to start 7 letters of comment, then we say 7 comment, and then 0 to say this structure is over. But we can also do 1, the first C, 4, then 4 more letters. This will be put together as C comment. You see what I mean? And it's very important that both the commands, the actual commands in the file, or the pixel data are using the same structure. So basically, you cannot jump over anything longer than 255 bytes. So basically, you can say, hey, ignore this entire frame. But on the other hand, you can, any length that is non-null is a jump to something next. And you can even say, hey, let's jump. If you jump to, even if I jump in the C is not null, so it will jump further. So if there is no null value at all, we will always jump further, which is weird, but that's a very good way to abuse randomness. But that's not how we're going to do it. Now, because image data and extensions are both using subblocks. So basically, you have a comment that either stops here, either extend to the first image of the data of the first frame, and basically the comment will then be resumed in the image data. And this idea was suggested by Mark Stevens after he looked at the specs, and that was extremely brilliant. So basically, that's the generic image, the generic idea. Now we have either we declare a command that jumps into the image, which makes the whole first frame ignored, taken as a comment, and then the second image is parsed. Or instead, we have the shorter command and with the collision. It stops here, and then the first frame is displayed for 10 minutes, and hopefully no one sees the next frame, which will eventually appear. But that makes it exploitable, even though there is this restriction of cannot jump over more than 255 bytes. And this is exploitable by FastColl. By FastColl, not by Unicoll. So we define a command. We specifically give a length so that the next length will be here. We don't know the value again, but we can do some post-processing to know where this chunk will end eventually. Oh, there's the palette. So we have to locate the 21 FE, which is the 21 will be the exclamation mark. And we see we have exclamation mark to F, and then we jump to F, and we jump on another start of a command, and so on and so on. That's a 7B, and so on. Again, every non-null value is a jump, and we end up makes a GIF a bit weird because you don't have a proper length. You just need to hop from one subblock to the next. So the same structure is used for data. So you can use it to jump over the first image, and you just put a very long delay of many minutes. And after 10 minutes, the images are identical. Now, if you want a common header, there will be a problem for the dimensions, but at least you can reach FastColl, so it's super fast to recompute. So, and you normalize the palette of both files to put them so that you can, because again, as you mentioned before, the command can be only after the global palette. So instead, put the palettes inside. I mean, it depends where you want to jump, but if the palette is big, then you will have a problem to be able to jump over the palette of the first frame. So maybe put the palette of the first frame as a global, and for the palette of the second frame, then it's what I want to say. No, yeah, you need to jump to the if the palette is here, if the first frame has a local palette, then it will be between the command and between the image data, which may be too big to jump for 255 bytes. So basically, the palette of the first image, the first frame, is in global, and the palette of the second frame is local, so that you can reliably jump from the command to the palette, the pixels of the first frame, which makes it a bit complex. Exploiting FastColl is a rare thing in a reliable way. I mean, FastColl as it is, but yeah, it's so combine two frames in single animation. But that's a good thing, right? If you combine an animation, they share the palette. Then you extend the command to a line. You compute FastColl, and this time you will compute FastColl for every pair, but it's fast. So it shows that it's usable, but it's definitely not that flexible. So that's an actual example. The declaration, a jump, and then you keep jumping inside the file, inside the collision blocks, and then depending on what you got, you end up crafting the rest of the structure of the file so that everything ends up being parsed properly. So that was a difficult feat, not the easiest exploitation, but also a bypass of the 255 bytes limitation. That was a great idea for Mark Stevens once again. So, what did SHA-1 break? BitTorrent indexes blocked with SHA-1. Subversion servers were unexpectedly broken. Is that link still live? Apache Subversion is enabled to store SHA-1 collisions. This adversary is still there. And Mark Stevens created the SHA-1 detection collision library, and we'll actually cover that in the next stream. SHA-2, clearly invisible from Mark Stevens' perspective. Let's see what the future is about. But at least the same file format tricks will be reusable. Protocols can be attacked, sloth, but also more recently last year with a specific, because fast collision, a new collision by Mark Stevens for the Radius protocol. So that was longer than I thought. And yeah, if you have no questions, then I will see you next stream. And unlike my initial plan, I will cover hash coins and detecting hash collisions in the next streams. That will be much shorter and probably more fun or exploring crazy hash collisions. So yeah, very interesting topic. Thank you for the stream. I'm glad you liked it. Yeah. What else? No other questions? I have all the files under me. Oh yeah, I also need to do the inside out hash collisions. So that will be for the next stream. Hash coins, that would be good enough for a new next stream, I guess. So thanks a lot for your attention. No other questions? And yeah, so have a nice day and see you next stream. Bye, everyone.